Hello everyone, welcome to the Puff Academy lecture. In this chapter, we're going to talk about one of the most widely adopted hardware security certification standards today, FIPS 140-3, and its related certification program called CMVP, which stands for the Cryptographic Module Validation Program. This slide sums up the relationship among the four key parts. FIPS 140-3 is the current standard, officially replacing FIPS 140-2. It builds on the foundation of FIPS 140-2, but updates the requirements to reflect modern security needs and international standards alignment. While FIPS 140-2 defined the earlier minimum security requirements for cryptographic modules, FIPS 140-3 refines and expands those requirements. CMVP is the program that validates a cryptographic module against that standard. And CAVP, the Cryptographic Algorithm Validation Program, remains the program that validates the cryptographic algorithms themselves. CMVP, run by the US NIST and Canada CSE, continues to use accredited labs to test your product against the current standard and issue certificates confirming compliance, whether your module is hardware, firmware, or software. Because almost all security functions still depend on cryptography, the correctness of each algorithm must continue to be validated independently. That's where CAVP comes in. CAVP tests implementations of cryptographic algorithms like AES, SHA or SAECDSA, and many more, and issues algorithm certificates. These certificates are then included in the CMVP submission as key evidence of conformity under FIPS 140-3. You can simply think of this way: FIPS 140-3 is the current standard. CMVP validate your whole commercial cryptographic modules, and CAVP validates the algorithms you use. Together, they ensure that both your overall module and its cryptographic algorithms meet today's recognized security requirements. Now, we've just seen how CMVP and CAVP work under the FIPS 140-3 framework. Let's dive into the FIPS 140-3 overview. NIST stands for the U.S. National Institute of Standards and Technology. It's the agency that publishes information security standards and guidelines. FIPS, which means Federal Information Processing Standards, are a series of mandatory standards issued by NIST that cover both algorithm specifications and application requirements. FIPS 140-3 doesn't tell you exactly how to design your module. Instead, it defines the minimum security bar and the verifiable criteria your module must meet. Some of the key areas it covers include module boundary and composition, a clear definition of what's in hardware, firmware, and software, access control, key management, physical tamper resistance, etc. But the question is, what does FIPS 140-3 contain? FIPS 140-3 defines security levels 1 through 4 to indicate the strength and depth of protection a cryptographic module must achieve. In principle, each higher level includes and tightens the requirements of the previous one. Let's walk through each level step by step. Level 1 is the baseline. Compliance focuses on approved cryptographic algorithms and security functions. No physical security or user authentication required. It is typical for software crypto modules in OS crypto libraries. Level 2 is about tamper evidence and role-based authentication. It requires adding visible tamper evidence seals or enclosures. Supports role-based access such as admin versus user, without identifying individuals. Level 3 is tamper detection and identity-based authentication. It requires adding active tamper detection such as abnormal voltage or clock with immediate response such as key zeroization. Authentication recognizes individual identities, not just roles. Level 4 is full environmental monitoring. It asks continuous monitoring for extreme conditions like temperature, radiation, or EMI. Must zeroize sensitive data or enter safe states to resist attacks, even in hostile environments. By understanding these levels under FIPS 140-3, you can better match your product's security goals to the appropriate certification target. Now we know the 140-3 defined requirements, but how do we make those requirements testable and verifiable? CMVP is the process that turns FIPS 143's requirements into something you can actually test and prove. FIPS 140-3 lays out what security capabilities a module must have, and CMVP uses accredited third-party laboratory testing to verify that your implementation and manufacturing processes truly meet those requirements. Now, you might be curious that who runs CMVP and how is it validated? Vendors work with the laboratory accredited under NVLAP, that's NIST's National Voluntary Laboratory Accreditation Program, to perform the testing. When you pass the test, the lab produces a detailed report based on FIPS 140-3 and its derived test requirements, often called the DTR, and submits it for joint review by NIST and Canada's CCCS, part of CSE. Once approved, the module is listed on the CMVP validation list, and you will receive an official certificate from the authorities. Okay, let's look at what kinds of products actually go through this process and which security levels they tend to target. This slide gives you a real-world snapshot. The first message is that there's a wide variety of products pursuing CMVP validation under FIPS 140-3. The pie chart on the left shows typical product categories: line PC, routers, faxes, etc. The second message is about which levels dominate. The distribution on the right indicates that Level 1 accounts for roughly a quarter of all validations, while Level 2 and Level 3 make up the majority. Level 4 is rare, largely because of its much higher testing difficulty and the very stringent requirements for physical protection and environmental monitoring that FIPS 140-3 enforces. A simple summary to help your product development is: Levels 2 and 3 are the mainstream targets for most enterprise and government procurements, balancing cost, schedule, and assurance. Level 4 is typically seen in HSM, which stand for Hardware Security Module, or specialized high-protection scenarios, for example, key management hosts or defense-grade equipment. Achieving Level 4 demands stronger tamper detection and response as well as active monitoring of environmental anomalies like temperature, voltage, or electromagnetic interference, which drives both design and validation costs up substantially. If your product is not intended for risk environments, prioritizing Level 2 or Level 3 often yields the best cost-effectiveness. By contrast, HSM class products more commonly aim for Levels 3 or 4 to align with their role in protecting critical keys. Alright, we've just talked about which kinds of products seek CMVP validation and what security levels they usually target. Now let's move from where and who to what. What CMVP actually validates under FIPS 140-3. FIPS 140-3 defines 11 core security requirements. These are the pillars that CMVP labs and reviewers will examine in your submission, and for each item you must provide clear, testable evidence. Let's walk through them step by step. The first is the cryptographic module specification. You need to clearly describe where the module begins and ends, what it's made of, and what security functions it provides. A publicly available security policy is also required so that both users and reviewers understand exactly what's in scope. Then there are the ports and interfaces. Every input and output has to be classified: data inputs, data outputs, control inputs, and status outputs. The key idea is to prevent sensitive information from leaking through the wrong channel. At higher assurance levels, you may even need physical separation of certain interfaces to make sure they can't be misused. Roles, services, and authentication are another critical piece. You have to define who can access the module and what they can do. At Level 2, it's enough to say this person is an admin, or this person is a user. But starting at Level 3, the system must actually verify the identity of the specific individual. A finite state model shows how the module behaves step by step. For example, when you power it on, it runs self-tests, then moves into normal operation. If something fails, it must go into a safe state and block sensitive operations. You can't skip those checks. Physical security grows stricter as you move up the levels. At Level 2, it's tamper-evident seals. At Level 3, the system actively detects tampering and wipes keys if it sees an attack. At Level 4, the module has to keep monitoring the environment for things like extreme temperatures, voltage fluctuations, or radiation, and react immediately if something looks wrong. The operational environment is also important. If your module runs in a general-purpose operating system where code can be changed, you need strong controls to ensure only trusted code runs, updates are handled securely, and privileges are enforced. If it's fixed firmware, the rules are simpler. Design assurance is about process discipline. You need configuration management, proper documentation, version tracking, and quality control so the module can be reproduced consistently and reliably. Next is key management, which covers the entire key lifecycle. How keys are generated, stored, distributed, used, and eventually destroyed. The policies around key attributes and zeroization have to be crystal clear. You also need to show compliance with EMI/EMC requirements. That means the module shouldn't emit signals that leak sensitive information, and it must be resistant to outside electromagnetic interference. For self-tests, the module has to check itself both at startup and during operation. Common examples include algorithm known answer tests, key pair consistency tests, continuous RNG tests, and firmware integrity checks. If any of these fail, the module has to shut down securely. Finally, you must address mitigation of other attacks. This covers things like timing attacks, power analysis, electromagnetic side channels, and fault injection. You should explain what countermeasures you've built in, whether that's detection, adding noise, masking, or wiping keys when anomalies are detected. These 11 categories are the core areas CMVP will examine under FIPS 140-3. When you prepare your submission, map your security mechanisms, test evidence, and process documents to each requirement so reviewers can quickly see how you comply. Now let's step back and answer a very practical question. How is the overall level of your module actually determined under FIPS 140-3? Under FIPS 140-3 and CMVP, each of the 11 requirement areas is rated independently at a level between 1 and 4. The overall module level is determined by the lowest rating among those 11 areas. Let's look at the example on the right table. If even one area is only at level 2 while the other 10 areas are at level 2 or 4, the overall level is still level 2. Think of it as the weakest link sets the ceiling. So your design and your submission must avoid single-point weaknesses that could drag you down. So why does level 4 feel so far out of reach for most companies? The picture at the bottom of the slide makes it clear. The hardest jump is actually just getting from untested to level 1. At that point, you're not just tweaking something, you're building the whole foundation, defining the module boundary, writing full documentation, putting in self-tests like known answer tests, setting up key management procedures, and proving design assurance. That's a lot of work if you're starting from zero. Once you have level 1, moving up to level 2 or level 3 is more of a steady climb. You add visible tamper protection, then tamper detection and response, and you upgrade authentication from role-based to identity-based. In other words, you're strengthening on top of what you already built. But the moment you try to go from level 3 to level 4, the slope gets much steeper. Level 4 means continuous environmental monitoring, immediate reaction to any anomaly, much tougher physical countermeasures, and a mountain of evidence to prove it all works. That translates into higher design costs, more complex manufacturing, and way more testing. That's why, under FIPS 140-3, very few products ever make it to level 4. Now, we've reached the last part of our FIPS 140-3 journey, so let's step back and see the whole picture, from getting ready to earning the CMVP certificate, to actually using it in the market. It all starts with design and production. As a vendor, you have to define your module boundary, finish the design and manufacturing, and pull together the required documents, things like your security policy, design evidence, and test results. You also need to secure CAVP certificates for all the cryptographic algorithms you'll rely on. The next stage is cryptographic technology and security, short for CTS lab testing. You send your module to an NVLAP accredited lab, and they validate it against all 11 requirement areas of FIPS 140-3, everything from algorithms and self-tests to physical security and key management. The lab then writes a detailed report. That report goes on to CMVP for review. This is a joint effort between NIST and the US and Canada's CCCS. If they agree the lab's findings check out, NIST issues your certificate and your module officially goes on the CMVP validation list. Finally, there's market adoption. Once you have that certificate, you can promote the modules level, remembering it's defined by the lowest level achieved across the 11 categories, and you can use it to satisfy government and regulated industry requirements. That validation becomes both a trust signal and a ticket into certain markets. Thank you for watching Puff Academy's lecture. We look forward to seeing you again soon.